The selection committee is pleased to name Dr. Noah Mandel, a 2022 Frederick A. House Scholar in Computational Science. Noah finished his PhD in Plasma Physics program at the Department of Astrophysical Sciences of Princeton University under the supervision of Professor Greg Hammett in 2021. After graduation, Noah joined MIT's Plasma Science and Fusion Center as a postdoctoral fellow. Noah's selection as a House Scholar reflects both his outstanding research achievements and his demonstrated leadership and character. During his doctoral studies, Noah conducted groundbreaking research which resulted in significant advances in plasma physics. Using his expertise in plasma physics, applied mathematics, and high-performance computing, Noah developed the first gyrokinetic turbulence code able to include magnetic fluctuations in the critical open field line region of tokamak. Noah also applied this novel computational model to conduct the first nonlinear electromagnetic simulations of turbulence in the scrape-off layer. This study enabled him to uncover important physics, for example, finding that the bending of the field lines caused by the expulsion of plasma blobs leads to a reduction in turbulent transport and an increase in intermittency. Noah's doctoral work included a number of other advances in computational plasma physics. He developed a spectral formulation of all phase space dimensions in gyrokinetics and implemented the resulting equations as the GX code for use with GPUs. The efficiency of the spectral approach combined with the speed of computation on GPUs gives GX the potential to be a game changer in the area of turbulent transport simulations, with speedups relative to more traditional codes of over an order of magnitude. See David's talk earlier about It could enable detailed studies of turbulence in regimes inaccessible to current codes, for example, turbulence at high beta and in non-axisymmetric confining fields, as well as cheaply providing the large number of transport simulations required for device optimization. Noah extended the capabilities of the computational models beyond the current state-of-the-art approaches and created tools that can have a big impact on the magnetic confinement fusion community. Noah also demonstrated himself as someone who deeply cares about the success of young scientists and is eager to make positive contributions to the scientific community and society at large. Noah served as mentor to several undergraduate students, both during his work with the PPPL Summer Internship Program and MIT's Summer Research Program. He has led efforts to extend computational capabilities of such widely used codes as Jekyll. And even outside of science, Noah's character also shines through, both in his efforts as treasurer of his undergraduate fraternity to fundraise for events such as the Special Olympics, and through his musical endeavors as lead saxophonist for the University of Maryland Jazz Ensemble. Noah's scientific excellence and leadership embodies the qualities of Fred Howes, encourage in all young scientists, and make him a deserving recipient of the Howes Award. So congratulations, Noah. Take it away.
Thank you very much. Thank you so much to the DOE CSGF and to the selection committee. So I'm going to be talking about my research, which involves fusion and trying to make fusion a reality. All right. Right, so fusion. Fusion is the energy that powers the stars. So it's as simple as you take some deuterium, you take some tritium, you smash them together, you get some helium, you get some neutron, and you get some energy, a lot of energy. It's easy enough in the stars, but it's challenging on Earth. So the development of fusion as a viable commercial energy source will be a game changer for the health of the planet in the coming decades because it's a clean and virtually limitless energy source. This energy source would have a minimal carbon footprint, no long-lived radioactive byproducts. It's safe. There's no meltdown scenario. So in stars, there's this enormous gravitational pressure that produces the conditions necessary for fusion. Here on Earth, we had to develop a different approach, which involves heating gas to something like 150 million degrees, which is 10 times hotter than the surface of the sun, so that random collisions of the particles will have enough energy to overcome the repulsive forces between the ions. So we do this with magnetic confinement fusion is one of the main ways that we've developed. So at these extreme temperatures, the fuel, these gases, become a plasma. So you just have a charged gas. And these plasmas can be confined by strong magnetic fields. The ion in this magnetic field is gyrating around the magnetic field, and you can confine the particles that way. And this allows us to confine the fuel and the heat in magnetic insulation. So the most advanced designs that we have are donut-shaped. This is a diagram of a tokamak. And so you see the magnetic field lines wrap around the donut and if I take a cross-section of this, you have the core where you want everything to be hot, and that's where you want the fusion to be happening. And those are closed surfaces there. And so you have this hot core region, and then you have the cool walls of the device. And the temperature gradients between this hot core and the cool walls is something like 1,000 times steeper than the gradients that are handled by spacecraft on reentry. So that's really challenging to deal with. So it is really exciting times in the fusion community. Recently, the JET experiment in the UK set a record of 59 megajoules of fusion power over 5 seconds. So here's the inside of the JET tokamak, and there's a guy in there, so you can see the scale. NIF also had a major breakthrough. So NIF does things a little differently. It's inertial confinement fusion, where they shoot some super lasers at a tiny capsule and implode it. And that produced 14 kilojoules of energy, which was more than the X-ray energy that was absorbed by the capsule. So that was kind of a break-even moment. But it's still a small fraction of the total laser energy that is going into this. Coming up, the community is super excited about ITER, which is a large experiment that's being built by a massive international collaboration. ITER will produce 500 megawatts of fusion power from 50 megawatts of heating power. So there will be a gain of 10, which will be a major breakthrough. And so you can see, so I showed you JET before. JET is the little guy in the bottom left corner. And you can see that the size of ITER it's 10 times bigger by plasma volume. Also very exciting is this new spin-off that came out of MIT called Commonwealth Fusion Systems. And they have started building the SPARC tokamak. SPARC is going to use stronger magnetic fields, which are enabled by this new high-temperature superconducting magnet technology, which will give similar performance to ITER in a smaller device. So their target is a gain of greater than 2, but it could go up to a gain of 10. And here's the fancy new magnet that they have developed that goes up to 20 Tesla. And this is projected to begin operation in 2025. So it might actually beat ITER to the real break-even moment, which will be very exciting. All right, so we have these exciting things coming up, but fusion is still hard. The problem is that we need to achieve and maintain these high pressures in the core to reach self-sustaining burning condition, so something like 10 times hotter than the surface of the sun. The first problem that we have is that heat gets lost too quickly from the core because of turbulence. So you have some turbulent mixing in here. Turns out that nature doesn't like temperature gradients that are that steep. And so you lose heat faster than it can be produced by the fusion reaction. Bigger reactors and strong magnetic fields, like in these upcoming devices, can help. A second problem, major problem, is that the heat that comes out of this then gets exhausted in the boundary region, where the field lines actually intersect with the device walls. And if too much heat is coming out in too narrow of a channel, you could melt the metal plates down here, which would be bad. So we need a simultaneous whole device solution to these couple problems. And so that's where I get into whole device modeling and optimization. So this is somewhere where exascale high-performance computing could make a large impact in the success of fusion by enabling the design of more efficient reactors. So for a given reactor, we would like to be able to model and predict things like the fusion power, which is determined by some macroscopic profiles of density and temperature in the core. So if I take some line out of the core here and I draw the pressure profile, so this is peaked in the very center, and then it goes down. So the pressure that you achieve here is related to the fusion power that you're going to get out of the device. And so these profiles are something that we'd like to be able to predict for some given configuration. And then we also need to be able to know about the boundary properties, namely, are we going to melt the walls or not? Stuff like that. And so I've been developing models that both work in the core. I'll tell you about GX and Trinity. And also in the boundary, so that's Jekyll. All right, so fusion is hard, but modeling a fusion plasma is also very hard. And part of the reason that that's the case is that a fusion reactor has an enormous range of scales. On the small scale, we have turbulence, and so you can see a little picture of a turbulence simulation here. And then many orders of magnitude in both space and time up, we have our slowly varying background profiles. And so, this several orders of magnitude is challenging to do. And you also have to take into account that at the very high temperatures that our plasma is at, you need a kinetic description. You can't just rely on simple fluid. So that means you have to solve a PDE in something like 5D. And so if you think about spanning this whole range of scales in 5D, say, if this would be the number of grid points that you might need in 5D as you were trying to resolve all these micro scales across the whole macro scale. And then if you consider that how many flops that would take. So if your method went like n squared and you had to resolve all of this time, that would be this many flops, which would require something like the time of the universe to simulate on an exascale computer. So obviously that's not possible, and so we need to be more clever. We need to be able to use these exascale kind of resources, but we also have to have clever algorithms in theory to get this down to a more tractable number. And then if you want to even go to the optimization context, you would want to do, I don't know, 100 or 1,000 of these kind of calculations, and so you need even more acceleration. All right, so right. So here's what an advance that we've made in terms of using a multi-scale approach to model this. So here's my temperature profile again, but now I'm going to not just look at it in space, but also in time. So you can imagine this profile evolving on some time scale that's on the order of seconds. And so if we used this brute force approach where we took a fine mesh in both space and time, you can see how many grid points that would take. The multi-scale approach is to zoom in on these small areas and only use a fine grid to model the turbulence in these little patches, which are then embedded in a coarse grid that we can evolve the slower dynamics on. And so this will dramatically reduce the domain over which our fine mesh is needed. And so these little patches are orders of magnitude smaller in both space and time than the big grid. So GX is a turbulence code that I've been developing, which is going to be the thing that zooms in those little fine patches. And that solves a 5D PDE in time. And so it can predict things like the turbulent heat flux that comes out of some surface in the plasma. We're using pseudospectral methods, so it's Fourier in space and Hermite and Laguerre in velocity space. And these methods are ideal for GPUs because the compute intensity is mostly in fast transforms and tensor operations, and GPUs really like those kind of crunchy things. And so the code has been designed and implemented directly in CUDA and C. And you can see here something like a 5 to 8 times speed up of the code over some state-of-the-art calculation that is running on 88 CPU cores compared to a single GPU here. So that's pretty good. And then you couple that with our velocity representation seems to have better convergence properties, which means that we can use maybe 7 times less velocity resolution and still get the same answer. So whereas if we use the same resolution as this state-of-the-art, which is I'm now comparing 256 CPU cores to a single GPU. At the same resolution, this is maybe twice as fast, but then we can scale down the velocity resolution and get to something like 10 to 15 times faster than this state-of-the-art, which is really great. And then so we can put this inside a transport solver. So what's happening here is we're basically doing GX calculations at each of these grid points. and then tying them together. And so this is a transport solver that ended up taking 10 large transport steps in this multi-scale algorithm. It resulted in something like 288 nonlinear turbulence evaluations with GX. And this whole thing took about 2 hours on 16 GPUs. And so this is really exciting. This means that we can use this kind of transport model to predict the profiles and optimize them for future experiments. And then what about the edge? So I've told you about the core, and now we need to think about the edge. So Jekyll is a model for the edge region, the boundary region. So modeling the boundary requires even more specialized codes. We can't use the same multi-scale approach we used in the core. And so Jekyll is specialized for this. We use an energy-conserving discontinuous Galerkin discretization scheme. And one of the central contributions of my thesis work was a novel scheme that models electromagnetic fluctuations in the plasma. And this code is massively parallel, scales to thousands of CPUs, and we're working on a GPU implementation too. So a little bit about DG. DG is a class of finite element methods with discontinuous basis functions. So you can see here a piecewise constant representation. You can go up to piecewise linear, piecewise quadratic, so on. And these are really nice methods because they're highly local, highly parallelizable. They allow this high order accuracy, and they can enforce local conservation laws. So if we take our system, which can be generically written like this, and we represent our solution F with some basis expansion, we're using a modal expansion, a modal DG scheme here. And our fundamental DG operations can be represented as some tensor product. So you do an integral over some cell in DG, where you're projecting some term onto the basis functions. And if you express it like this, you end up with some tensor, which involves some inner product of the basis functions times the solution elements. And if we choose our basis to be orthonormal, this tensor will be sparse. So that's what we do. And we actually use a computer algebra system to compute these sparse tensor products analytically and write the code for us. So this is what that actually looks like in our code. So we have this sparse tensor, which all of these numbers are just elements of this sparse tensor, and then you have all the elements of the alpha and F arrays here too. And so this has been generated by Maxima. It takes advantage of the significant sparsity of this tensor contraction, whereas this might be this many multiplications and additions naively, but if you take advantage of the sparsity, you reduce it down significantly, and it made the code something like 30 times faster than an old version that did something more naive. And these kernels have a really high arithmetic intensity, which is ideal for modern computing architectures. All right, here's a nice movie for you. So this is showing blobs of plasma in our scrape-off layer, and they propagate radially outwards. The physics behind this is similar to Rayleigh-Taylor instability, where you have a heavy fluid falling into a lighter fluid. And the turbulence that we're seeing here can spread out the heat flux footprint that flows along these open field lines down to the diverter plates. And so here's the heat footprint, and showing that turbulence can actually spread this out, which would be good. Here I'm going to show you some of the ways that the plasma interacts with the magnetic field line. So if I take my domain, which is a helical simulation domain, and I'm going to straighten out this helix for visualization purposes, so it's just going to end up being a straight box like this. And say we have some blob of plasma. As that blob moves, it will bend magnetic field lines with it. So magnetic field lines in a plasma behave like taut strings. And those field lines can actually be plucked by the plasma motion, like I'm trying to show here. And so I'm going to show you on the next slide a video of this with lots of different field lines moving around. I'm going to show you a view that's looking down on the field line like this, So you're going to see like a perpendicular cut of this. I'll also show you a view on the top, looking down like this. Right, and so if this is a field line that I'm drawing here that kind of bows out in this projection here, it might look like this little curly Q here. So you can see the electron density fluctuations in the background here, and you can see blobs, and as they move out, they're actually grabbing onto field lines and bending them and pushing them around. And so this is kind of a neat visualization of some of the first-of-a-kind capabilities that I developed in my thesis. So now we have GX and Trinity in the core, we have Jekyll in the edge, and so we have a model that we can use to model the whole device. So this would allow us to study, the interaction between the core and the boundary, and see if solutions that we have for mitigating the heat fluxes in the boundary would negatively impact core confinement or something like that. And so as we add more physics to these models, we'll achieve true predict-first modeling capability. We're not done yet, though, because we would like to do optimization, and optimization at exascale was the title of my talk. And so to do that, we need to make sure that our whole device model calculation is actually sub-exascale, maybe petascale. And so this requires both algorithmic advancements and effective use of latest hardware like GPUs. So what would be great is if we had each whole device calculation could compute key figures of merit, like the total fusion power or confinement time or the heat load to the walls. And then we could vary something like 20 different shaping parameters and determine how these things affect these figures of merit. And you could imagine a parallel optimization algorithm that runs something like 10 to 100 of these configurations simultaneously and scaling up to kind of an exascale kind of calculation with this. And using a hierarchy of models of varying speed and accuracy to narrow the design space progressively. It's not all just a pipe dream. We actually have done some of this. So we did a preliminary design study where we were varying the shape of our plasma just in the core. So we were varying the elongation, how elliptic this shape is, and we were also varying the triangularity. So most tokamaks that exist today have a D shape that points radially outwards, but now people are investigating D shapes that face radially inwards. And our optimization study, which did something like 18 design evaluations, which required over 8,000 nonlinear turbulence calculations and ran 3,000 GPU accelerated node hours. It moved around in this design space, and it decided that a negative triangularity configuration was actually optimal, and it achieved something like a 90% increase in fusion power per unit volume by going to this negative triangular configuration. And this is actually consistent with recent experiments that were actually done after we published this that show the same thing, that confinement is actually improved with negative triangularity. So this is pretty cool. Okay, to summarize, I've presented a whole device framework for modeling turbulence and transport in fusion reactors. So I have GX modeling the turbulence in the core with spectral methods on GPUs, and it couples to a transport solver called Trinity to do multi-scale core transport modeling. And then Jekyll is going to be working in the boundary, doing turbulence with discontinuous Galerkin methods and first-of-a-kind kinetic scheme that includes magnetic fluctuations. A number of key advances have been made here, spanning theory, algorithms, and hardware. And there's still work to do, but we can achieve game-changing whole device transport modeling and optimization to design better fusion reactors. Thank you so much again to CSGF. This work would absolutely not have been possible without the generous support that I received. Also, quick plug for PPL. If this talk sounded cool to you, go to PPL for your practicum. There are many researchers there that are doing world-class computing, so please come talk to Stefan and I at the DOE lab poster session this afternoon. And here are a few more acknowledgements. Thank you.